Good morning and welcome to a new VoltLog. In today's episode I'm going to upgrade the lights over my workbench using some LED strips. These are the 7020 rigid aluminum base LED strips that I showed in a previous video. As discussed in that video, the LEDs used on these strips contain a single die, although you can find these in a dual die option as well, but probably for a higher cost per LED strip. But before we start, I would like to mention my appreciation towards the guys from gearbest.com because they sent me a free power supply and LED dimmer to use in this project. They asked if I needed any products for my current projects, and as I was working on this project, I requested a power supply and a wireless dimmer. The first thing I would like to do is to take a look at the inside of this power supply and check its overall construction. The model of this power supply is T15012, and that probably means it's 150 watt at 12 volts, and it doesn't appear to have a specific manufacturer specified on this label. So let's go ahead and open this power supply. It seems that we only have these 4 screws keeping the top cover on. So now about the construction of this power supply, I'm only going to talk about the choice of components and the construction quality. It seems we have a model number written on the PCB and a date, which is probably the design or manufacturing date. That's 2013. Starting from the left, this is the AC input, which by the way is kind of universal, 110 to 220 volts. We can see a very small fuse in there, glass fuse, right behind this connector. Then we have the filtering X cap and the Y cap. We also have an NTC. We have the common mode choke filter and the bridge rectifier together with the main filtering cap, which of course is going to be a one hang low brand. I'm not even sure I can read the brand of this one because it's kind of celested. Now I can't see the brand on this capacitor, but I'm quite sure they're not using some well-known capacitor brand in here. Continuing, we have some passives on the input of the transformer. The transformer, by the way, looks to have a decent amount of copper inside. We do see an optocoupler in here, which is of course going to be separating the hot side from the cold side. We also see a Y cap, which is usually put across the two sides to filter out some noise. And towards the right side of this power supply we have 4 filtering capacitors. Let me see if I can read the brand on these ones. If I'm correct, these are Chong capacitors. So quite a nice name for these Chong capacitors. Right here next to the output terminals we have an LED for checking if the power supply is outputting something, and an adjust potentiometer for a fine adjustment of the output voltage. The PCB seems to have only through-hole components on this side. I don't think there is anything on the other side. It's not quite the cheapest PCB material that you find. It's not really that phenolic type PCB material. It looks more like an FR4, but not quite as good quality as an FR4 should be. As we can see in here, initially they wanted to use 2 vertical caps, but they probably switched last moment to this 90 degrees bent larger single capacitor, and it is actually 120 microfarads at 450 volts for the main filtering cap. The overall construction is this U-shaped aluminum, which seems to be aluminum alloy, and the active components are bolted to the case to ensure required cooling. But I'm sure for my application this power supply will do just fine, because I'm only using 4 of these LED strips, and it should be pulling about 1 amp from the power supply. So in total 4 amps required from this power supply that should be able to output up to 12.5. So we're only going to stress this power supply at 30% of its limit. For securing the LED strips to the actual holder slash heatsink, I'm going to use this heatsink plaster, which is basically a thermal compound with added adhesive properties. So I don't have to use any screws or clamps to keep the LED strips attached to the heatsink. The heatsink plaster will just harden and secure the LED strips to the heatsink. I'm going to try to do this off camera because it's kind of difficult to get that even layer of thermal compound all the way on the length of the strip while on camera. So this is how the LED strip looks like with the thermal compound. Now I'm going to try to apply it to the heatsink. I am applying some pressure to the LED strip just to make sure they're making perfect contact with the aluminum heatsink. Alright, this looks good. So now all I have to do is repeat the process for the right side. I have 4 pieces of 50 cm LED strips in total on this heatsink, each requiring 12 volt. So they require constant voltage to be applied, and for that I have them connected in parallel at the middle point, so each strip doesn't need to carry more current than what it needs for its own length, and that I measured to approximately 1 amp. Let me tell you, it's not easy to solder on these things because they are basically a solid piece of aluminum attached to a heatsink, especially if you're using a crappy soldering iron like I am. The problem with the cheap soldering iron is that it can't maintain the temperature at the tip, so as soon as you touch your soldering surface, the temperature at the tip drops and it will struggle to rise again, but that might take some time. Unfortunately, good quality soldering stations are quite expensive, so not so easily accessible to hobbyists like myself. As you can see in this picture, I used 2 pieces of quality silicone wire to snake my way around the contacts of the LED strips so that each of the 4 LED strips gets both a positive 12 volts and a ground. Now regarding the RF LED dimmer that I have, I recommend that you connect it as close as possible to your LEDs or LED strips, because this thing works by using a technique called PWM on the LED power lines, and that is very likely to spread RF noise sent through some long lines. So by connecting the LED dimmer right next to the LED strips, the PWM signal will travel through very short wires and will send less noise into your space. Just for a quick test, I hooked up the power supply, and it appears that the power supply is outputting 12.3 volts. So I'm going to adjust it to output exactly 12 volts. Alright, that should do it. And just as a quick note, there is a very tiny LED in there that I mentioned earlier when we opened the power supply. That's a 3mm green LED, but it's not turning on. I'm not sure why it's not turning on, but I think it should be on to signal the power supply is working. So maybe just a factory defect, I don't know. Unfortunately, the dimmer that I installed, the one I got from gearbest.com, seems to be working at some frequency that is audible. I mean, anything less than 100% brightness, aka going into dimming mode, will produce this audible sizzling noise coming from my power supply, and I'm pretty sure it's caused by the frequency at which the dimmer does the PWM. Running at 100% brightness setting doesn't produce any audible noise, but that's something you would expect because the MOSFET is fully on and not switching while in that mode. I do have another wireless dimmer which seems to have similar specs and size but just looks different on the outside, so I'm hoping this second dimmer is working at a different frequency, making none or less audible noise. Another solution would be to use one of those sealed brick type power supplies, because for those the plastic outer case acts as a sonic barrier and keeps the noise inside. Or in an application where you would install this power supply behind the wall or a ceiling, you would get the same soundproofing effect because of the wall. But for now I'm going to stick with this power supply, mainly because it's the only one that I have and meets the requirements of this project, and also of course because I got it for free. So I ended up using the second RF LED dimmer because it produces less, close to no audible noise in my power supply while dimming the LEDs. Also, as an added feature, I've added these two ferrite chokes on the input and output of the LED dimmer just to take the edge off that noise, which is inevitably being created and radiated around my lab due to the PWM applied to these high currents. The first thing I did after wiring everything up was to take some measurements of light intensity and temperature. First, let's talk about light intensity, where I got a very nice improvement. In this picture, where I'm using only the CCFL bulb lamp, which is directly above the meter at a height of 45 centimeters, same as the LED strip, as we can see I get about 750 lux. This is basically my old lighting lamp above my bench. Moving up, I turned the CCFL bulb off and the LED strip on at 25% brightness. Remember, the LED strip is at the same height of 45 centimeters relative to the light meter. As we can see, I get about 830 lux with a much better distribution of light across the bench. Next, adjusting the brightness of the LED strip to 50% brings the measurement at 1600 lux, and finally going all the way up to 100% brings the measurement up to 3300 lux, which, let me tell you, looks great on my workbench and especially coming from that angle. Next, the LEDs were left running at full brightness for about 15 minutes and measured the LED strip temperature using a thermocouple and my multimeter. The result is not great, as the LEDs reached about 62 degrees C, and that is with a 30 degrees Celsius ambient. Although the operating temperature of this LED chip might be up to 85 degrees C, while looking through various datasheets, I couldn't find a graph showing a plot of the expected life in hours versus temperature. If I were to guess, I would say you need to run this at less than 50 degrees C to get some decent life out of them. There was a mention of a stress test in a datasheet, and that meant for that particular LED manufacturer, running it at 60 degrees C, full rated current for 1000 hours with no resulting damage. If you have any info on these LEDs and what temperature they should be running at to get some decent life out of them, please leave a comment below. So, to finish up on this story, I have to say that I learned some things about these LED strips. If I were to design something from scratch, I would run some basic thermal calculations based on the figures from datasheets, but in this case, with these Chinese LED strips, there is no datasheet. I can't even easily compare to existing datasheets because these can't be compared. The driving current is different, the LED in my case has only one die, and so on. So the next thing I will try is to double my L-shaped heatsink with another piece, the same model and size. This way I will be increasing my heatsink surface and hopefully cool the LEDs better, maybe shave another 5 or maybe more than 5 degrees C. I will be posting an update with some measurements for comparison once I get the upgrade done. Links for the power supply, LED dimmers as well as the light meter used in this video will be in the description below, so do check them out. Thank you for watching this video, feel free to leave a comment below or hit that like button if you enjoy it. See you next time.